Have you ever wondered how your computer manages its memory? Today we dive into a common memory management issue called fragmentation. Picture this: you're trying to pack a suitcase, but instead of one large space, it's divided into smaller compartments. This makes it difficult to fit in larger items, even if there's enough overall space. That's a bit like fragmentation in operating systems. It's a situation where memory gets inefficiently used due to how it's allocated and deallocated over time. This can lead to a drop in system performance, a decrease in available memory, and overall inefficiency. Much like the suitcase scenario, it's all about how the space is divided and used. So understanding fragmentation is key to understanding how computers maximize their memory usage. Stick with us as we delve into the types of fragmentation, their causes, and how they're managed. Now, let's get into the specifics of this phenomenon. Fragmentation comes in two main types: internal and external. Let's start with internal fragmentation. This happens when a process is allocated more memory than it actually needs. Imagine you're baking a cake and you take out a whole bag of flour, but you only use a small portion. The rest of the flour in the bag is like the unused space within an allocated memory block. It's there, but it's not being put to use. This typically occurs when memory is allocated in fixed-size blocks, and there's a mismatch between the size of the block and the actual memory requirement of the process. Now, let's move on to external fragmentation. This is when free memory is divided into small, non-contiguous blocks. Think of it like trying to park a car in a crowded parking lot. There might be enough total space for your car to fit, but the spaces are scattered all over the lot and aren't big enough for your car to fit into any single one. The same thing happens with memory. Even though the total free memory might be sufficient, it's challenging to allocate larger memory segments because the free memory is broken up into smaller non-contiguous blocks. This often results from frequent allocation and deallocation of memory blocks of varying sizes. Both types of fragmentation can cause inefficiencies in an operating system's memory management. Internal fragmentation leads to unused space within allocated memory blocks, while external fragmentation makes it difficult to find large enough contiguous blocks of memory to allocate to processes. So, we've seen that both types of fragmentation can cause inefficiencies. But what leads to these issues in the first place? Several factors can contribute to fragmentation in operating systems. First up, let's talk about variable-sized memory allocation. In essence, this is when memory blocks are allocated and deallocated at different sizes. It's like trying to fit different size puzzle pieces together. Sometimes they just don't align perfectly. This mismatch can lead to external fragmentation, with memory being split into small, non-contiguous blocks. Then we have static partitioning. Picture a big cake cut into equal slices. Now imagine that not everyone at the party is equally hungry. Some might only eat half of their slice, leaving the rest uneaten. This is similar to what happens in static partitioning, where fixed-size memory blocks are allocated to processes. If a process doesn't need all of its allocated space, the leftover chunk results in internal fragmentation. Next, there's non-contiguous allocation. This is when memory is allocated in scattered blocks rather than one continuous piece. Imagine trying to park a long vehicle, but instead of finding one big parking spot, you have to park it in small slots scattered all around. It's inefficient and can lead to external fragmentation over time. Finally, frequent memory allocation and deallocation can also contribute to fragmentation. It's like a revolving door of memory blocks being continuously used and then freed up. This high turnover can lead to both internal and external fragmentation, as memory blocks are not always allocated and deallocated in a tidy, orderly manner. These factors, either alone or in combination, can cause fragmentation in operating systems. It's a bit like a game of Tetris. If the blocks, or in this case, memory allocations, don't fit together neatly, you end up with gaps and wasted space. But remember, fragmentation isn't just an abstract concept. It has real-life implications, impacting the efficiency and performance of systems we use every day. These factors result in fragmentation, but what are its real-life implications? Fragmentation can have significant effects on your computer's performance and efficiency. Let's dive into the specifics of these impacts. Firstly, fragmentation can lead to reduced memory availability. This is particularly due to external fragmentation. Think about it this way. Even when you have ample free memory, it's divided into small disjointed blocks. These blocks are scattered all around, making it a real challenge to find a continuous memory block for allocation. It's like trying to park a bus in a busy lot where only compact car spots are available. Next, let's talk about performance. Here, internal fragmentation is the primary culprit. When processes are allocated more memory than they need, the leftover space goes to waste. This wastage is similar to buying a large pizza when you're only hungry enough for a slice. The remaining slices, or memory in our case, are unused and lead to a decrease in the overall system capacity. Then there's the issue of increased resource utilization. To manage fragmented memory, your system needs additional overhead. This means your CPU and memory are working harder than they should, just like a traffic cop directing cars around a roadblock. This extra effort leads to higher resource usage, which can slow down your system and reduce its efficiency. Finally, fragmentation can add a layer of complexity to memory management. The operating system needs to keep track of all the scattered blocks of free memory. It's like trying to solve a jigsaw puzzle where the pieces are spread out across the room. This requires additional logic and data structures, adding complexity to the operating system. Clearly, fragmentation can cause problems. But don't worry, there are ways to minimize it. So let's stay tuned to find out how you can keep your system running smoothly. There are several strategies that operating systems use to minimize and manage fragmentation. One popular strategy is compaction. Compaction works by moving memory blocks around to consolidate free memory into larger contiguous segments. It's a bit like tidying up a cluttered room, where you move things around to create more space. This strategy effectively reduces external fragmentation. However, it's worth noting that compaction can be resource-intensive, as moving memory blocks around requires time and processing power. Another common approach is using paging and segmentation. Paging is a method where memory is divided into fixed-size pages. This reduces external fragmentation because it prevents the creation of small, non-contiguous blocks of free memory. On the other hand, segmentation allows logical division of memory based on the size of the process. This helps reduce internal fragmentation, as each process gets precisely the amount of memory it needs, reducing the amount of wasted space. We also have allocation strategies like the best fit and buddy systems. The best fit strategy allocates the smallest block of memory that still fits the process's requirements. This approach minimizes internal fragmentation by ensuring that each process only gets the memory it needs, and no more. The buddy system, on the other hand, divides memory into blocks of power of two sizes. This system allows for efficient splitting and merging of memory blocks, reducing external fragmentation. These strategies do more than just reduce fragmentation. They also improve overall system efficiency and performance. By reducing wasted space and ensuring that processes can access the memory they need, these strategies help your computer run more smoothly. They also reduce the additional overhead required to manage fragmented memory, leading to lower CPU and memory usage. To sum it up, fragmentation is a common issue in operating systems that can lead to decreased system performance and memory availability. However, with the right strategies, we can minimize and manage fragmentation effectively. So, these strategies help manage fragmentation and keep your computer running smoothly. We've covered a lot today, from the types of fragmentation to the techniques used to manage it. We've delved into the world of memory management, highlighting the causes and impacts of fragmentation. We've discovered that fragmentation, both internal and external, can lead to inefficient memory use, decreased system performance, and increased resource utilization. We've also understood that the causes of fragmentation are varied, from variable-sized memory allocation to static partitioning and non-contiguous allocation. But as we've seen, there are strategies to mitigate these issues, from compaction to paging and segmentation to best fit and buddy systems. Understanding fragmentation is crucial in managing and optimizing computer systems. It's a key concept in operating systems and a fundamental part of memory management. We hope this video helped you understand the concept of fragmentation. Thanks for watching, and remember to subscribe for more informative tech content.